Okay, we want to do an example now using all of this. We want to see how many electrons can go in every quantum state, all right? So we're gonna do an easy one. So let's just do it. Okay, let's say we start off with n equals 1. Now, if n is 1, what's L? Well, L goes from 0 to n minus 1. If n is 1, that means L is 0. So we have L is 0. Now, what are the possibilities for M? Well, M goes from minus L up to positive L, but L is 0, so just 0. Okay, and then what's MS? MS is always up or down, right? Plus or minus a half. So MS is plus or minus a half. Okay? So how many electrons are there? Well, 2, right? Because there's the possibility of up and down. So there's 2 electrons. So 2 electrons. 2 electrons. Okay? All right. And I'm just going to write this. You'll see why in a minute. Okay. So that was n equals 1. Now let's do n equals 2. All right. Now, what's the possible values of L? And n is 2, so we can only have 0 and 1. So we have L equals 0 and L equals 1. All right. If we have L equals 0, M sub L can only be 0, and MS is always plus or minus a half, right? So there's 2 electrons there, 2 electrons. Now, if L is 1, then we can go minus 1, 0, positive 1, right? So if L is 1, we have M sub L equals negative 1, M sub L equals 0, M sub L equals positive 1. And then MS is always plus or minus a half. Okay, so let's see. Here, all right, okay, so here we have 2 electrons, right? Here we have 2 electrons, because 2 electrons, and here we have 2 electrons. So how many do we have in the n equals 2? We have 8. 8 electrons. Okay. Now, you want to do n equals 3? Forget it. I mean, we could, but I ran out of board space. All right, but anyway, n equals 3 would be kind of a mess, right? We'd have L equals 0, L equals 1, then you have L equals 2, and you have to do all the different possibilities. Ugh, forget it. So I don't want to do it. Now, there are some definitions that they use when they do this kind of thing. So same n is a shell. So this is a shell, right? This is a shell, and this is a shell, right? So this is a shell. And that's why I wrote this. So we have 2 electrons in the shell. We have 8 electrons in the n equals 2 shell. Okay, then we have subshells. They have the same n and the same L. Okay, so let's see. So there's kind of some little things. All right, so this gives you the number of electrons. All right, so let's see if it works. So put in n equals 1. 1 squared is 1 times 2. Yep, it worked. Now let's try the n equals 2. So 2 squared is 4. 4 times 2 is 8. Yep, it worked. Okay. And then, I don't know, put L equal to 0. So you just get 0 plus 1 is 1. 2 times 1 is 2. Yep, 2. And you can keep doing. All right, let's do this one. All right. So we know for L is 0, we get 2. Let's do L equals 1. So 2 times 1 is 2, plus 1 is 3. 3 times 2 is 6. So how many do we have for L equals 1? for L equals 1, we had 6, right? 2 plus 2 plus 2 is 6. So all I'm saying is, so these formulas work. They can tell you how many electrons. That's why I didn't want to do n equals 3, right? Because for n equals 3, then for n equals 3, then I would have to have a L equals 2. So 2 times 2 is 4 plus 1 is 5. So I have 10. Forget it. I don't want to do that. But you can do it if you want. Okay. Now what's the big deal? Well, if you have a closed shell, in other words, if you have 2 electrons in this shell, it's going to be an incredibly stable atom. Okay? That's all there is to it, right? So it's going to be very tightly bound. If you have a closed shell, super stable. If you have a closed subshell, somewhat stable, all right? But this is the big one, okay? So there you go, all right? So again, this is the periodic table. Yeah, finally, all right? Periodic table. So elements with similar electron configurations, that means that they have similar chemical properties. And elements with similar electron configuration or chemical properties, they're arranged in columns. So look, what do you think? Helium, 2 electrons. Where are they going to go? Right here. So this shell is going to be completely full. So what does it mean it's going to be true about helium? It's going to be super tightly bound, closed shell, And so that means if it's tightly bound and it's has a filled up shell, it doesn't want to react with any other element, right? And if you really want to, you can work out the same thing with neon and argon and all of these. All of these in that column, all of their shells are full. So they're happy. They don't have any reason to react with anybody. And so basically, they're non-reactive and they're called the noble gases. The noble gases. You remember when we did that radioactive decay example in the chapter 42 with nuclear physics? I talked about argon, and I said that the probability of argon being in a meteorite initially is pretty small, because argon's a noble gas. It's not going to react with anybody. It's not going to be found in a meteorite. Okay, let's see. All right, this. Okay, look. How many electrons does hydrogen have? 1. How many does it want to have? 2. So what's it going to do? How's it going to get that other electron? It's going to react with somebody else, right? That has an extra electron. All right? So, so these guys want to react with somebody else, right? With another element. Okay? They want another electron to fill their shells. So they're called alkali metals. So they're very, very reactive alkali metals. Okay? This one here, come on. These here, oh, I'm sorry. Let me go back to this. Well, it doesn't matter. You can say that they have an extra electron if you want. All right, that's probably better. They have an extra electron, but the same thing as I said. They're highly reactive. Okay, these guys, come on. Okay, these guys, they are missing an electron. So they want to react as well, okay? And they're the halogens. So all I can say is this whole atomic structure thing explains this. It's as simple as that. The electron configuration explains that. All right, that's all I want to do for this chapter. So we interpreted the quantum mechanical solution for hydrogen, and we talked about the shell model. Let's just review. So this is the potential energy function for hydrogen. You stick it in the Schrodinger equation. You do the Schrodinger equation with spherical coordinates. You separate them into 3 differential equations. You solve them. You get 3 quantum numbers. Oh, you get applied to boundary conditions. No kidding. So you get 3 quantum numbers. Energy En minus 13.6 electron volts over n squared. Principal quantum number. Angular momentum is quantized. Magnitude L. H bar square roots of L plus 1. And it goes from 0 to n minus 1. And then you get the z component of the angular momentum what I call m sub L, right? M sub L goes from negative L in steps of 1 up to positive L. So that's just Schrodinger's equation. And people thought that was going to be enough. Ha ha, they were shocked, right? When they did the Stern-Gerlach experiment. With L equals 0, you expect this. Sorry, you get this. You get 2 lines where you expected 1. So that just basically means the only way you can account for that is if the electron has a magnetic moment. It acts like a little magnet. So that means, oh yeah, sorry. All right, so that means you have another quantum number, right? You have another quantum number, that ms, up or down. And then Pauli came along and he said, well, he noticed this. You know, this would be the normal kind of expected thing. But Pauli said, I mean, they looked at the data, and so Pauli said, look, what does this imply? It implies that you can't have electrons in the same quantum state. So that's the Pauli exclusion principle. All right, so here's atomic structure, right? 4 quantum numbers, 3 from the Schrodinger equation, 1 from the Stern-Gerlach experiment. And then you have the Pauli exclusion principle, and that is everything there is to know about atomic structure. And again, don't forget this. Spin is a horrible term. The electron is not spinning. Just remember that the electron acts like a magnet. It has an inherent magnetic moment. That's it. Thank you very much.